Hello everyone. Welcome back to our week number 2. My name is Anna Muzikina and I'm Google Developer Group Organizer. And today we will continue diving deeper into exciting topic artificial intelligence. And today we host speaker Kate Vyshydkevich. She is Women Tech Members Ambassador. She is a certified professional machine learning engineer, and she will explore machine learning and feature engineering today. And we will continue our study gems journey. But before we continue, I'd like to mention that we are super friendly and super supportive community. So please let's lift each other up without no tolerance or negative comments, jokes. We haven't no place here. Anything that put others down. It's space to continue growing, sharing technical knowledge, and grow up together as machine learning engineers. So I stop sharing. Kate, you are welcome. Please share your screen.
Do you see my screen?
Yes,
Can you hear
perfect.
me? Okay, thank you. Um, this week we will explore intermediate machine learning and feature engineering themes. Intermediate machine learning is the next step after learning the basics. It helps improve model accuracy and efficiency by handling missing data, automating workflows, and using advanced validation methods. These techniques help us move from beginner ML models to real world applications. Feature engineering is the process of transforming raw data into useful inputs for ML models. Well engineered features can significantly boost model accuracy and effectiveness. This course, Intermediate Machine Learning, addresses the challenges of real-world data, including missing values, non-numeric data, and data leakage. It provides techniques to enhance machine learning model quality. The course welcomed learners with prior machine learning background, aiming to elevate their model's performance. Practical application occurred through hands-on exercises using housing prices competition datasets involving 79 explanatory variables to predict home prices. Progress was measured via leaderboard submissions. The housing prices competition served as a practical platform allowing you to concept and track their improvement. In this lesson, three approaches to dealing with missing values were learned. The effectiveness of these approaches was then compared on a real-world dataset. Data can end up with missing values in many ways. For example, a two-bedroom house won't include a value for the size of the third bedroom. A survey respondent might choose not to share his income. Most machine learning libraries, including scikit-learn, give an error if you try to build a model using data with missing values. Therefore, strategies to handle these missing values required. The simplest option, dropping column with missing values. Unless most values in the dropped columns are missing, the model loses access to a lot of potentially useful information. An extreme example, a dataset with 10,000 rows where one important column is missing, a single entry was used to illustrate the loss of information. Imputation fills in the missing values with some number, while the imputed value won't be exactly right in most cases. It usually leads to more accurate models than dropping the column entirely. An extension to imputation, imputed values may be systematically above or below the actual values, or rows with missing values may be unique in some other way. In such cases, considering the values, which values were originally missing, could improve prediction. This approach involved imputing the missing values and adding a new column that shows the location of the imputed entries for each column with missing entries in the original dataset. This could meaningfully improve results in some cases, but not in others. The Melbourne housing dataset was used in the example. The model utilized information such as the number of rooms and land size to predict home price. The data loading step was not focused on. The functions core dataset was defined to compare different approaches to dealing with missing values, reporting the mean absolute error from a random forest model. It was concluded that inputting missing values generally yielded better results than dropping columns, especially when missing values were not overly prevalent. Categorical variables, which contain a limited number of distinct values, require preprocessing before being used in most machine learning models. We covered three primary methods: dropping categorical columns, ordinal encoding for variables with clean order, and one-hot encoding for variables without inherent ranking. Through the practical example of Melbourne housing dataset, we observe how these methods impacted model performance. While one-hot encoding generally yields the best results, the optimal approach can vary depending on the dataset and the nature of the categorical variables themselves. The key takeaway is the importance of understanding and effectively utilizing categorical data to build robust and accurate machine learning models. Pipelines essentially create a sequence of operations, making code more organized and efficient. While many data scientists build models without pipelines, pipelines offer several important benefits. Cleaner code pipelines simplify the management of data at each preprocessing stage. Fewer bugs pipelines reduce the risk of misapplying or forgetting preprocessing steps. Easier to productionize pipeline facilitates the transition of models from prototypes to deployable solutions. More options for model validation. Pipelines enable advanced validation techniques like cross-validation. The Melbourne housing dataset was used for the demonstration. It was assumed that the training and validation data were already loaded. This lesson demonstrates how to streamline machine learning workflows using pipelines. First, we defined preprocessing steps. The column transforming bundled numerical imputation and categorical imputation with one hot encoding into single preprocessing unit. Next, we defined our model, a random forest regressor. Finally, we created and evaluated a pipeline that combined the preprocessing and modeling steps. This allows us to fit and predict with a single line of code, ensuring validation data was consistently preprocessed. We evaluated the model using mean absolute error. Pipelines simply code, prevent data leakage, and make complex preprocessing more manageable, providing to be essential tools for efficient machine learning. Cross-validation is a technique to assess how well a machine learning model will generalize to an independent dataset. It addresses the limitation of a single validation split by dividing the data into k-folds. Each fold is used once a validation set, while the remaining folds train the model. This process provides a more stable and reliable measure of a model performance, reducing the impact of a random data partitioning. We use scikit-learn's cross-val score to automate cross-validation. This function handles the creation of folds, the training of model on each fold, and the evaluation. The scoring parameter allows us to specify the evaluation metric. We often use negative mean absolute error or negative MIE. This is because scikit-learn uses a convention where higher scores indicate better performance, and we want to maintain consistency, even though MIE itself is a measure of error. Cross-validation is particularly valuable for small datasets, where a single validation split may not accurately represent the data's variability. It reduces the impact of randomness in data partitioning, providing a more reliable measure of model quality and improving the model's ability to generalize to unseen data. While it's beneficial, we must consider the computational cost, especially when we're working with large datasets. In such cases, a single validation set might be sufficient. XGBoost or extreme gradient boosting is a powerful ensemble learning technique for a structured data. It builds on the concept of gradient boosting, iteratively adding models to an ensemble to improve prediction accuracy. We'll explore how extreme gradient boosting works, its key parameters, and how to optimize it for performance. Gradient boosting is an ensemble method that sequentially adds models to correct errors made by previous models. XBoost is an optimized version of its technique, known for its speeds and performance. It uses gradient descent to minimize a loss function, iteratively improving predictions by focusing on the errors of the current ensemble. XGBoost has several key parameters that significantly impact its performance. An estimator controls the number of boosting rounds. Early stopping rounds allows us to automatically find the optimal number of estimators. Learning rate scales the contribution of each model, affecting both training speed and accuracy. And jobs enables parameter processing, speeding up training on larger datasets. Tuning these parameters is critical for achieving optimal performance. XBoost is a leading library for working with structured data, providing high accuracy when properly tuned. Parameter tuning, especially adjusting the N estimators, early stopping rounds, and learning rates, is essential for achieving optimal performance and avoiding overfitting. By utilizing this technique, you can build highly accurate and efficient models. Data leakage occurs when training data contains information about the target that won't be available during prediction, leading to misleadingly high model performance. We'll explore target leakage, train test contamination, and how to identify and prevent these issues to ensure reliable models. There are two main types of leakage. Target leakage happens when predictors include data that won't be available at the time of prediction, like using future information to predict the past. Train test contamination occurs when validation data influences preprocessing steps, leading to over-optimistic model evaluations. Both types compromise the model's ability to generalize to new unseen data. Detecting leakage involves careful data inspection for suspicious relationships and ensuring proper separation of training and validation data. Using cross-validation and pipelines is crucial for preventing train test contamination. To prevent target leakage, exclude any variables that are updated or created after the target value is determined. By identifying and mitigating these issues, we can build models that perform reliably in real-world scenarios. Feature engineering is the process of creating new features or transforming existing ones to make data better suited for machine learning models. The feature engineering course focused on enhancing machine learning models' performance through strategic data transformations. It covered techniques to identify and create informative features, including using mutual information to rank feature importance, applying mathematical and group transforms, and leveraging unsupervised learning methods like means clustering or PCA to discover underlying patterns. Target encoding, a supervised method to effectively encode categorical features using target variable information. The main goal of feature engineering is to optimize your data for machine learning. This involves improving predictive performance, reducing computational needs, and enhancing the interpretability of results. A key principle is that features should have a relationship with the target that the model can learn. For example, transforming features to create linear relationship for linear model. To illustrate feature engineering, we use the concrete data set. We first establish a baseline model to feature initial performance. Then we create synthetic features like ratios of ingredients, which are often more predictive than absolute amounts. Adding these ratio features significantly improve our model's performance, demonstrated how feature engineering can expose valuable information to the model. Mutual transformation is a powerful metric for ranking features based on their relationship with the target variable. It helps us understand which features have the most potential for prediction, especially in datasets with many variables. We'll explore how mutual information works, its benefits, and apply it to the 1985 automobiles dataset. Mutual information quantifies how much knowing one variable reduces uncertainty about another. Unlike correlation, it can detect any type of relationship, not just linear ones. It interpreted in terms of uncertainty reduction or entropy. Essentially, it tells us how much information a feature provides about the target. We apply mutual information to the 1985 automobiles dataset using scikit-learn's mutual info regression. We label and code categorical features and then calculate ML scores. Visualizing these scores with bar plots helps us quickly identify the most informative features. We also use scattered plots to examine specific relationships like curb weight and price, confirming the insights gained from ML scores. Mutual information scores helps us understand the potential of feature as a predictor. Scores range from null for independent features to higher values for strongly dependent ones. Remember, most information is unvariate metric, so it doesn't detect iterations between features. The actual usefulness of a feature depends on whether your model can learn the relationship. Visualizations and domain knowledge are essential for interpreting and utilizing MI efficiently. The lesson focuses on feature creation, which is the process of generating new features from existing ones to improve the performance of machine learning models. This involvement transforming raw data into more informative representations that better capture the underlying patterns in the data. The lesson covered mathematical transforms, which included applying arithmetic operations to columns, such as creating a stroke ratio from engine data. Data visualization aided in suggesting transformations, such as using logarithms to normalize skewed distributions like wind speed. Count features were also created by aggregating binary or Boolean features to represent the presence or absence of certain attributes. Combining features like creating, make, and style revealed valuable interactions. Group transforms aggregated information across rows grouped by a category. For example, calculating average income by state using group by and transform. This technique allowed for the creation of features like frequency encodings. When using training and validation splits, independence was preserved by creating grouped features on the training set and merging them with the validation set. The choice of feature creation techniques was determined by model strengths and weaknesses. Linear models benefited from sums and differences, while tree-based models excelled with count features. Normalization and the potential of interaction effects were considered when creating new features. This lesson introduced clustering where K-means unsupervised learning technique for feature engineering. Clustering involves assigning data points to groups based on their similarity, aiding in the discovery of underlying data structures. When used for feature engineering, cluster labels can simplify the complex relationships. Chi-means clustering, which uses straight line distance, Euclidean distance, in other words. The algorithm interactively assigns points to the nearest centroids and then moves these centroids to minimize distances. Key parameters like n clusters, m iter, and m init were discussed, emphasizing the importance of choosing n clusters through hyperparameters tuning. The concept of creating Voronoi station to visualize cluster assignments was also covered in this course. The lesson demonstrated the application of k-means clustering using the California housing dataset. Latitude, longitude, and med-inc were used to create economic segments. K-means was applied with cluster 6, and the resulting cluster labels were added as a categorical feature. Scatter plots visualized the geographic distributions of these clusters, showing distinct segments for higher-income coastal areas. Box plots were used to analyze the distribution of med household within each cluster, demonstrating that the clustering effectively separated data points based on median house values. This example highlighted how clustering can transform special features into meaningful categorical variables, improving model performance by simplifying complex relationships. Principal component analysis (PCA) is an unsupervised learning technique that partitions the variations in data, revealing underlying patterns. It transforms original features into principal components, which are linear combinations of the original variables representing axis of variation. Each component's loading indicate how much each original feature contributes. Principal component analysis is useful for dimensional reduction, anomaly detection, noise reduction, and decorrelation. The Abalone dataset illustrates how principal component analysis can identify size, shape components from height and diameter. Understanding the explained variance and loadings is crucial for interpreting principal components analysis results. PCA is typically applied to standardize data to focus on correlation. Principal component analysis is useful for dimensional reduction, anomaly detection, noise reduction, and decorrelation. Lesson demonstrated PCA using the 1985 automobiles dataset, focusing on highway MPG, engine size, horsepower, and carb weight. The data was standardized before applying PCA. The resulting components were analyzed for their loadings and explained variance, revealing a luxury economy axis in PC1. Mutual information scores of the components were examined to identify predictive variations. For example, PC3 highlighted a contrast between horsepower and carb weight, suggesting a sports car versus wagon distinction. A new ratio feature, sports or wagon, was created to capture this contrast. This example illustrates how principal component analysis can be used as a descriptive tool to discover meaningful relationships and create new features based on the identified variations. PCA's sensitivity to scale and to the importance on handling outliers were also emphasized. Target encoding is a supervised feature engineering technique that encodes categorical features using information from the target variable. It replaces categories with values derived from the target, such as the mean, offering an alternative to one hot or label encoding. Mean encoding, a simple form of target encoding, calculates the average target value for each category. However, this method can lead to issues like overfitting and handling unknown or rare categories. Smoothing techniques such as M-estimate addresses these problems by blending the category average with the overall average, reducing the impact of noisy and or infrequent categories. Lesson demonstrated target encoding using movie lens M dataset, focusing on the high cardinality zip code features. A 25% split was created to train the target encoder, ensuring independence and preventing overfitting. M estimate encoder from the category encoders package was used, with the parameter M set to control noise. The encoded zip code feature was then compared to the rating target using distribution plots. The plots revealed that the encoded feature effectively captured useful information as its distribution closely mirrored the target's distribution. This example highlighted the effectiveness of target encoding for high cardinality features and its ability to reveal informative relationships between categorical features and the target variable. This course emphasized the importance of understanding data through domain knowledge and visualization, and provided practical examples to demonstrate how feature engineering can significantly improve model accuracy and robustness. So next is a homework for you for next week. So this course about machine learning, please. We also put it in Discord, so don't worry. Intermediate machine learning, please learn. Also, course about feature engineering. Those are Kaggle courses. They're very important for machine learning. And also Code Lab course from Google Cloud. Just a minute. It's optional homework. If you want, you can do it. So, thank you all for participation. Remember to complete your homework on Kaggle. Those are very important courses. Very interesting platform, Kaggle. Thank you.